Yeah, so I found this problem in the book, 103 out of 5.5. It's a good little problem. The average sales of this function. I'm using this F average formula here, and here we go. How do you integrate a 7450? 7450 T. Yeah, that's how you do it. Right. Hey, now, to me, this is a separate term, so it's kind of like a separate integral over here. That's how I would think of it. Look, I think of this as two separate integrals, but I don't bother to separate it. I just do this integral. Good job. Did the integral of him require any use? No, it was easy, right? Okay, now I'm going to integrate this. And to me, it's a separate integral, and I think now I need some U-substitution. It ain't much, though, U-substitution. Look, how did I do this integral? Remember this one? I integrated the sine of 4x. Ultimately, the answer is the negative cosine of 4x, but it did spit out a 1/4 from the U-substitution. All right, so if you don't mind, I'm going to use that idea and just take a little shortcut on this one. What do you think the U-substitution ought to be on this one? That angle, yeah, good job. That angle, pi t over 6. And if I take du, well, I was going to do a shortcut. I was going to do it in my head. Now I'm writing it down. If I take the derivative, I get pi over 6 dt. What ends up coming over to the other side, or coming out front, is the reciprocal of that pi over 6. You know, what came out in front of this was a 1/4. Well, what comes out in front of this is the reciprocal of pi over 6, so it's going to be a 6 over pi. So I'm going to have 43.75 times 6 over pi. By the way, this constant sits out front. And I'm integrating. Now I'm sort of doing it in my head. After I wrote down those ideas, I realized it's going to spit out a 6 over pi. What's the answer to the integral of sine? Negative cosine pi t over 6. I think I just integrated that. I integrated sine and I got negative cosine. And I spit out a 6 over pi. Why did I spit out a 6 over pi? From the U-substitution. Same reason I spit out a 1/4 over here. Are you with me? Same reason I spit out a 1/4, I'm spitting out a 6 over pi. I hope you understand that. Okay. Okay, now it's over. I need to plug in a 0 and a 12. Don't forget, is there something else out in front of this integral?
Yeah, the 1/12.
Oh, thank you. There's a 1/12 out in front of this integral. Okay. When I get this all done, it's a number. What is this number? The average value of the sales of this seasonal product for the whole year. Let's try it. There's 1/12, and I plug in a 12 here. That means I got 7450 times 12 plus whatever this is, negative, I might pick up a calculator and just try something. What is 43.75 times 6? Oops, times 6 divided by pi. I'm going to go ahead and decimalize this. I get 83.556. Is that what you get? In front of this cosine. And what am I doing? Plugging in a 12. Hey, what's 12 pi over 6? 12 pi over 6? That's a 2 pi. What's the cosine of 2 pi?
1.
That's a 1. Thank you. That's a 1. I should have just said 1, but anyway, I'll get back to that. That's the cosine of 2 pi. Minus, what else am I doing, you guys? I just plugged in a 12. Now what? Plug in a 0. That's 1/12 out in front of that. And now I'm plugging in a 0. If you plug in a 0 right here, it is 0. And if you plug in a 0 there, you get the cosine of 0. The cosine of 0 is not 0. It's something. It's a 1. So there's something there. Hang on a second. Hang on a second. I'm plugging in a 0 there. You're saying that's a 1. And so I get negative this number. What was this number? 83.556. Times 1. By the way, this is also a 1. This is pretty wild. Check this out. I mean, just a bunch of damn numbers, and maybe you guys just add numbers. But I see little patterns going on here. Like if I distributed this 1/12, it would cancel with this 12. What would I have here? I'd have 74/50. And what's this? I'd have this negative 83.5556 over 12. Do you agree with that? Negative 83.556 over 12. Do you agree with that? Mm-hmm. Yeah. And then what's going on over here? You see the negative signs? I think I have a positive. I think I have a positive 83.556 over 12. Well, guess what? We're done. Guess what the answer is? 74.50. I should have just known that from the beginning. Save myself some work. I'm totally kidding. Sort of kidding. That was kind of fun. It wouldn't be, you could try A and B. A and B, this was C. C wanted the entire year from 0 to 12. A and B do different amounts. They go from 0 to 3 and 3 to 6. You could try those. They won't be 74.50. They'll be different, I think. But for the entire year, it's 74.50. I don't know. I think it's a good problem. I like to try to apply these problems. There's a lot going on here. I wanted to remind you of this average value thing. I wanted to do one of those problems. I also wanted to remind you of this U-substitution here. How did we integrate this dude? It spit out a 6 over pi, you know? It spit out a 6 over pi from U-substitution. I know, I want to just share some more thoughts with you if you don't mind. This is a trig function. Can you tell me its period? Can you tell me its period? Well, the period is this. It's 2 pi divided by the number. No, it's 2 pi. If it was just a sine t, the period's 2 pi. But with that pi over 6, the period has been shrunk, or the pi over 6 has altered the period. And the way you calculate the new period is you take the old period, 2 pi, and divide by that number, pi over 6. So 2 pi divided by pi over 6 is the period of a trig function. The old period divided by that number. Hey, watch what happens. If you flip this up, you end up multiplying by 6 over pi. The pi's cancel, and this answer is 12. The period's 12. That means it goes through its whole cycle in 12. By the way, this was the sales of some seasonal product. Maybe over a year it does its cycle. Maybe it's seasonal. Maybe the fall, the spring, the summer, and then it does it again. Maybe it makes sense that the period is 12 months. And it does its thing. It does its cycle. Okay, do you know the amplitude of this sine function? It's a sine function and it has an amplitude. The amplitude's that number. So it goes up to 43.75 at its peak, and it goes down to 43.75, negative 40 at its lowest. So it looks like this. It's a sine function and it looks like this. Oh, except for one other thing. So that's 43.75 and this is 43.75, except for one more thing I forgot to do. I'm trying to graph this dude. I'm doing it without a calculator because I know stuff. One more thing though. I should add this dude. If I add this 74.50, what's that going to do to it? Shift the whole damn thing up. So it's this picture shifted up, so it won't be, well, let's see, what will be its new high point? When you add 74.50 to it, its new high point will be, can you help me please, 74.50? I can't do everything. 81.25? No. 74.50. 118.25. Thank you. I just added 74.50 to it. Thank you. If I add 74.50 to this, where does it put me, please?
$30.75.
30.75. Okay, thank you. So the new graph looks like this. It starts, no it doesn't, it starts in the middle. Where's the middle? 7450? See, this is 7450 plus that amplitude and minus that amplitude. And here we go. It's this sine function. Now do. Stare at that picture and tell me what its average height is from 0 to 12. 7450. Of course, we just did it. But just stare at the picture. Forget the math. Well, don't forget the math. But it spends half its time above 7450. It spends half its time below 7450. Equally so. And so I would say the average height is 7450. From 0 to 12. Because we did its whole period, it turned out to be that average height. If we just did 0 to 3, its average height would be, you know, I don't know, some number in between there. And it wouldn't be an actual. It wouldn't be the middle of those numbers. It would be some number in the middle, though. You guys okay with that? 0 to 3, the average height would be something else. 0 to 6, the average height, 0 to 6. Oh, they didn't do 0 to 6. They said 0 to 3. They said do that, and then they said do 3 to 6. That would be somewhere in here. Should be the same as 0 to 3, maybe. Huh. Whatever it is. Anyway. Interesting concepts, I think. What else did I want to do here? Look at this question. I hate to do your homework for you, but oh yeah, I better do one of these. Yeah, I better do one of these. Look at this, number 76. I'm in the homework. I'm in 5.5. I'm in 5.5. Here's number 76. It's an integral, and it is from 1 to 5, x over the square root of 2x minus 1. From 1 to 5, x over the square root of 2x minus 1. Okay, this is good, you guys. This is more advanced U-substitution right here. So, you ought to try it. You ought to try it. I'll try to help you. So the problem is just do the integral, please. Just do the integral. It happens to be a definite integral. We know the answer is going to be a number. The answer is some number. Bad rags or really good markers. It's hard to tell which. You know what I'm saying? You know what I'm saying? Damn. All right. A sticky board. Something. One of those three things. All right. What do you think, dude? This is a good problem. Any ideas?
The U-substitution should be 2x subtract 1.
I think so. He wants to let u equal 2x minus 1. I mean, that's a good place to start, sure. Okay, so what's du? 2. You could just say 2, but it's actually 2 dx is what it is. That's how you do it. All right, cool, man. I'm going to start replacing this crap. You know, one thing I like to do is move the 2 over here. So 1/2 du is dx. So I start replacing. It's replacement, you guys. Now, that denominator then is going to be the square root of u. And that dx out there on the end, that dx is going to be a 1/2 du. I'll put the 1/2 out here and put the du here. So I just replaced the denominator. I replaced the dx, you know, with these two ideas. Damn it. There's an extra x hanging around. When there's an extra x hanging around, you should say, damn it, there's an extra x hanging around. and then you should do something about it. What should you do about it? You need to turn it into u's. I mean, you can't have these x's mixing with u's like this. You need to turn that x into u's.
Use the equation.
You can go back to your original statement here and try to solve 4x in terms of u. You add 1, u plus 1, divide by 2 is x. See, you establish the u and x relationship. But you need to solve 4x in terms of u sometimes, because sometimes there's an extra x that needs to be replaced. So that x gets replaced with u plus 1 over 2. How you guys doing? Any questions? I mean, this is a good place to pause. I took care of all the u substitution and I got the integral rewritten. Now I gotta work on this integral now. But I've done the substitution part of it correctly. I'm good here. And I think I can do it now. I think again I got some ideas that sometimes you guys don't have. I want to pull out another 1/2. I don't know if you would have thought of it like that or not. But that's a 1/2 sitting there, and I want to pull it out. And it multiplies by this other half, so if you don't mind, that's a 1/4. And now I got u plus 1 over the square root of u. I got that, get that 2 out of my way like that. It is a 1/2. I mean, it's a 2, but it's in the denominator here, so it's a 1/2. Okay, do you know what to do now? We've done stuff like this before. Some people, what?
Change the square root into a half.
Yeah,
power.
yeah. It's u to the half. That's true.
Put it in the separate.
Move it up and call it u to the negative 1/2.
Yeah.
Then what? That's good. That's all good ideas. Hang on. You're saying u plus 1, and you move this up. It's u to the negative 1/2. You're right. Okay. Now what?
Distribute.
Yeah, definitely. Distribute before you integrate. Some students fall in this trap. They think, oh, okay, now I can integrate him and integrate him. Nobody ever told you integrate a product like that. It's a bad assumption by students. Don't do it. You don't integrate him and integrate him. You don't integrate products. You don't. So you distribute and then you integrate. Exactly. If I distribute and integrate, then I got 1/4. Oops, wait a minute. It's still an integral here. Hang on. I need my integral symbol because I haven't integrated yet. All I'm doing is playing, manipulating, form fitting, and eventually I'll integrate. When you distribute that, you add exponents. I think you get u to the 1/2. And then when you multiply times the 1, I guess you got u to the negative 1/2. All right, I'm finally ready to integrate, I think. I distributed and I added those exponents. So, to integrate u to the 1/2, you add 1. You know the rule, but sometimes you fail. It's 3/2 when you add 1 to it. It's 3/2, and then you divide by 3/2, but I multiply by 2/3. Cool. This guy, you add 1 to it. When you add 1 to him, he's a 1/2. And then you divide by 1/2. But instead of dividing by 1/2, I'll multiply by 2. Don't forget, there's a 1/4 in front of this. And I should put I was about to put a plus C, but hold on a second. Remember, this problem originally was a definite integral. What was the definite integral?
1 to 5.
Oh yeah, 1 to 5. But hold on. I want to say something. I sort of quit writing the 1 to 5. The reason I quit writing it, because it wasn't really appropriate for me to put it on here, because that 1 to 5 are bounds for x. And when I changed variables into u, it's not really appropriate to put the 1 and the 5 on there, because those are x bounds, and I'm now in u. Are you listening to me? This is important. The bounds are for x, and you did this change of variable, you did this u substitution, and now you're in u's. So those old bounds, 1 to 5, don't work on u. Okay, now wait a minute. When I get done with the problem, which I am done with the problem, I turn it back into x's? Yeah. Okay, well if I turn this back into x's, then it's, here we go. 2/3, what was U?
2x subtract 1.
2x minus 1 to the 3/2, and then 2x minus 1 to the 1/2. Okay, now I'm back in x's. I think I will evaluate it from 1 to 5. I will evaluate from 1 to 5. This is how you do a definite integral. You got to fight through the integral, that was a hell of a good U-substitution problem right there. That was a good one. We finally got it. It took several steps, but we finally got the integral done. We put it back in x's, and we can put these bounds on it. And then it'll be a number. Like I said, in the end, it's a number. Ready? I'll try to help you. There's a 1/4 out here. When I plug in the 5, it's 10 minus 1, which is 9. If you don't mind, I'm going to do some of this in my head. That's a 9. You know what the square root of 9 is? The square root of 9. That's what that is. Square root of 9? 3. Cubic. 27 times 2/3. 18. Good job. Let's plug a 5 in here. You ready? Plugging a 5 in here. It's 10 minus 1. It's a 9. What's the square root of 9? 3 times 2. 6. That's a 6. That was awesome. Minus 1/4. And now I plug in a 1. Plug in a 1. Plugging in a 1 is 2 minus 1. That's a 1. What's 1 to the 3/2?
1.
Say 1. Thank you. Times 2/3 is a 2/3. Plus, when you plug a 1 in there, that's 2 minus 1. It's a 1. The square root of 1 is a 1 times 2. That's a 2. Woohoo! There's the answer. I mean, I should finish it, but I'm so happy I got there. That's 24 divided by 4. That's 24 divided by 4. That's a 6. Get a common denominator. That's 8/3 divided by 4. I think that's 2/3. So that's 6 minus 2/3. Everybody knows that's 16/3.
Yeah.
Woohoo, baby! We got it. That was my number on the high school basketball team. I mean, I know, well, it was weird. Yeah, well, it was weird to be a fraction, 16/3. But I didn't play that much. I was on the bench. But when I told the coach, and you know, I said, listen, I want to be 16/3, but when you put it on my jersey, I want you to put this.
Oh my God.
Well, isn't that 16/3? Thank you. That's what we just proved. Right. I mean, either way, it's weird, right? All right, listen. So there was a couple points going on here. Listen, the point was this was a good U-substitution problem. It took some finagling. It took some creative solving for x in terms of u to replace that extra x up there. There was an extra x in this problem that was causing me issues. I had to replace it, and then I had to fight through this integral here. And we did it. The other issue was it was a definite integral, and so these bounds are for x. So please get back to x before you use the bounds. That's important. But I want to show you something. There was another way to do this. You can leave your answer in u's, and you could evaluate with your new u bounds instead of your old x bounds. Let me show you what I mean. The relationship between u and x is right here, you guys. Now watch. If x was a 5 and x was a 1, that's what they are. That's what they were, right? That was my lower bound and upper bound, 1 and 5. If I use this relationship right here, I can find the corresponding u values. I mean, when x is 1, plug it in, what's u?
1.
Oh, u happens to be 1. That's just a coincidence. Okay. When x is 5, what is u? 9. So what I could have done is once I change this into u's, now it's okay to put the 1 to 9 here now if I wanted to. And then I could carry that all the way down. Now hold on. when the integral gets done, which is here, I can evaluate this from 1 to 9. Because these are u bounds, and I can plug them in for u. You with me, right? It's very logical. So it's one or the other. I'm not really advising one's better than the other. I tend to go back to x's and use the original x bounds. That's what I tend to do. But you can stop here. Don't go back to x's. Get your answer in u's and use your new u bounds that you find by this relationship here. You can change your bounds into u's. But anyway, don't mix that up. Right? Don't go back to x's and then use u bounds. I mean, use x bounds on x or u bounds on u. Right. By the way, it's the same thing. You know, plugging in. I mean, you can see it now, can't you? Plugging in the 9 and the 1. Remember, I plugged in a 5. When I plugged in that 5, what did I get? I got a 9 and a 1. When I plugged in a 1, I got a 1. Right. So, right, you can see that it's the same, I guess, especially after I did it. Anyway, that's your choice, kind of. Cool. Any questions? All right, well, listen, I'm easing into 5-7 here. And I've already sort of been here. And by the way, this showed up on your quiz. What did I have on your quiz? Oh, there was a lot of stuff.
Oh, wait.
There was a 5 over x. And anyway, when you integrate, this is easy. This is just, you pull the 5 out. You don't even have to pull the 5 out, but you pull the 5 out. It's a 1 over x dx. A 1 over x dx is a classic. It's ln of x, right? So this answer is 5 times the ln of x. Technically, when you do these, you need absolute value on here. Sometimes I'm not too picky about that, but it's part of the formula. All right, so I'd like to do a little tougher one. How about this? Can't make it much tougher, can I do that? Look, I don't even know how to make this tough. Watch.
Pull the 5x squared.
Anyway, I tried to make a tough one. So what do you guys think? Talk to me. What do you think?
Can you pull the 5x squared over x squared out?
Yeah, I don't know about that. I don't think I like that way of talking. I think you need U-substitution. So what do you think U should be? All right, no. All right, hold on. So the theme in 5-7 is they're teaching you about this log integral. And I just did this 1 over x dx. It's a natural log. 1 over x dx is a natural log. Remember, we talked about how if you tried to move it up and do a power rule, the power rule fails. For most x's, you move it up and do a power rule. But this guy, when it's a -1, you move it up, you try to add 1 to it, the power rule fails. So he's got his own little rule. The derivative of 1, the integral of 1 over x is log x. And therefore, see, then you generalize that rule and you say the integral of 1 over u du is the natural log of u. And so then when you're in section 5-7 and you're sort of trying to apply this rule quite frequently, that's what's in 5-7, then you're kind of mostly letting u equal the denominator. But even without that big speech, you kind of should know that. I mean, you should let u equal the denominator because when you decide what u is, your brain ought to be already thinking what du is. It helps a lot. It helps you see the whole process. So you're thinking about u being an x cubed kind of thing. What's du? An x squared kind of thing. Dude, that's perfect to wipe out that numerator. I mean, watch how this works, right? You let u equal x cubed plus 100. Please tell me what du is now specifically.
3x squared.
3x squared dx. I know the 3 and the 5 don't jive. I know they don't jive, but when the constants don't jive, it doesn't bother me. I'll pull them out somehow. What I'm so happy about is having that x squared dx there to help replace that. Let me see how this is going to work. Here we go. I'm replacing this integral now. The 5 I'll pull out front. What about that denominator? The denominator is a u. And what about that circled stuff that I call x squared dx? What is it? What is x squared dx? Oh, it's right here. It's 1/3 du. Okay, so how do I replace it? I'll put 1/3 du right here. Actually, I like to pull the 1/3 out. And now this, you look at this and you say it's du over u, but that's the same. It's 1/u du. I mean, we're done. We're into a form, and we know his antiderivative. His antiderivative is log u, with a 5/3 out front. Thank you. So the answer is 5/3 the natural log of x cubed plus 100. I mean, it's a classic U substitution problem, but with u in the denominator, it produces this 1/u du is natural log u. We need this new rule, kind of. It's a lot in 5-7. How you guys doing? All right, I got more to say. There's more to this. We're getting toward the end of this course, though, but there's more to say here. Look at this. They throw these at you in 5-7. Check this guy out. Dude, this is horrible. You ready? I mean, it ain't really horrible. I'm sorry. I just like to scare you. Scare you into studying. It's not really a great technique. Well, I'm just going to spill the beans. You ready? Listen. I need to do long division. And that would be good advice. Anytime you have an integral and an integrand where the numerator has a higher degree than the denominator, it's kind of like an improper fraction. You know, I mean, 8/5, aren't you real tempted to call that 1 3/5? Well, nowadays we just call it 8/5. But you do. Anyway, it's like an improper fraction, kind of I'm saying when the degree is higher in the numerator than the denominator, that it's kind of an improper fraction. And in order to integrate it, I think I need to do long division. It'll make the integral a lot easier. I can't really figure this dude out like it is. So I have to go over to my scrap paper and do what's called long division. I have to divide x plus 2 into x squared plus 8x minus 13. You guys know how to do this? This is an old algebra idea from way back. You could do synthetic division as a shortcut to this. I'm just going to do this long division if you don't mind. But synthetic division is sort of a shortcut. You can't always do synthetic division. That's why I want to show you the long division. The synthetic doesn't always work. So here you go. Here's how you do it. You know how to do it?
X.
How many times does x go into x squared?
Once.
Yeah, and the way you say it is, maybe the best way to say it, I say, how many times does x go into x squared? Maybe I should say, what do you multiply by x to get x squared? X. So x goes into x squared x times. Then you multiply and you get x times x, which is x squared, and x times 2, which is 2x. And if you remember division, you know the next step.
Subtract those.
Subtract. Subtract. So now I'm subtracting these, or one way to subtract is change the signs and add. That's subtracting. Go back to first grade for a second here, but here we go. So this is gone. It's supposed to be. This is 8x minus 2x, which is 6x. Bring down the negative 13, and we continue our division. How many times does x go into 6x? 6 plus 6. So plus 6. 6 times x is 6x. 6 times 2 is 12. It's a positive 12. Don't forget now you subtract. So please put your subtraction symbols there. This will be gone. And this will be negative 13 minus 12. That will be negative 25. And an x can't go into negative 25, so that's your remainder. And you write your remainder over your divisor like this, plus a negative 25 over the divisor x plus 2. You remember that? I think I just sort of did that with my 8/5. Well, didn't I do that with my 8/5? What did I do? I divided 5 into 8. How many times does it go in there?
1.
1. With a remainder of 3?
Yes.
With a remainder of 3?
Yeah.
And what did I do with my remainder?
Put it over.
I put over my divisor. It's 1 3/5. I don't know. That's what you do. So it's a little bit of a pain in the ass. I mean, it's long division, you know? But it wasn't. It's not really the worst thing in the world. But I'll tell you what it did. It sure made this integral a hell of a lot better. This integral did look like this. But I did the division, so now the integral looks like that quotient up there, that answer. X plus 6 plus negative 25 over x plus 2. Dude, this is so easy now. It's so easy now. By doing long division, I transformed this into this. And now you can integrate it. You ready? By the way, to me, it's like 3 different little integrals here. It's all, you know, it's 3 different terms, you know. So can you integrate the x?
1/2 x. Yeah.
Yeah. That's how you do it, right? Integrate an x. Okay, can you integrate a 6?
6x.
Okay, good job. So you're 2/3 of the way through. Now you're integrating this. I'd like you to, let's think about him just a second here. He's got this x plus 2 in the denominator. Let's think about him a second. Any ideas?
U-substitution.
Good. I would call that a U-substitution. In fact, I'm going to go over here and blow this up for you. So let's blow this up a little bit here. Yeah, I'm saying the denominator is my u. I think this is u equals x plus 2. Can you please tell me what du is? Just a 1 dx, right? Just a 1 dx or just dx, that's good. Dude, that's very nice. When I plug this stuff in, let me see what I got here. The negative 25 can come out front. That leaves me a 1 over u. A 1 over u
dx.
du.
du.
du. You guys okay? It's very simple u substitution. Maybe I should have saw that in my head. That it's just a 1 over u du. And so how do you integrate a 1 over u du?
Natural log.
Natural log of u. So this is just a natural log of x plus 2, right, you guys?
Plus c.
Yeah. So let me go back to here, back to here. So my answer is x squared over 2 plus 6x, and we just did this. The answer is negative 25 ln x plus 2 plus c. That was not bad. After you do the long division, this is not bad to integrate. It probably involves a remainder like this, and the remainder is probably an ln type integral. So there's some of these in your homework. All right? All right? You guys okay? All right, I got more to say. I'm in 5-7, and one thing that happens in 5-7, when you get exposed to these log kind of problems, all of a sudden they teach you how to finish doing some of your trig that you can never do. So listen, we can now integrate tangent. We never could integrate tangent until we learned a few things here, but now we can integrate a tangent. But it takes a little work. You know your trig identities? Can you think of a way to get, I'd like to have a denominator. I'm in a denominator mode. I'm going to change it to sine over cosine. That's what I'm trying to get at, sorry. I want to change it. A tangent is a sine over cosine. That's an identity you should know. And now I think I want to do u substitution. I want to let u equal the denominator. I want to let u equal cosine x. What is the derivative of cosine? The derivative of cosine. Negative sine x? Right. So negative sine x dx. Dude, are you happy? Say yes. Just say yes.
Yes.
Yes, you're happy. When your du is the extra crap in your integral. It wipes it out. This is going to be beautiful. This is so nice. You ready? I mean, do you understand that now what we have is, let's see, what's my denominator? A u?
Yeah.
Okay, what is this circled stuff? Basically, it's my du, except for the negative sign, which I think I'll move over here, so I'll call it negative du.
Yeah.
So I'll put a negative sign out front. Are you guys okay? So now how do you integrate a du over u?
Natural log.
Natural log of u with a negative sign out front. Negative natural log of cosine x. That's the integral of tangent. It's kind of weird, but that's the integral of tangent. Maybe you should memorize that that's the integral of tangent. Your book presents it to you like, okay, here's your new rule for tangent. But you know, it doesn't matter to me whether you memorize it or not if you know how to do it. If you see a tangent, you could memorize that this is the answer. Or you could do it. It's not that hard to do. You know, some books will say this is the answer.
Yes. Yes.
So it looks completely different, but it's the same. Can you tell why it's the same?
Cosine of x to the negative 1 power.
Because of log properties, you could take this negative 1 out front and move it up here like an exponent. So now it's the cosine function to the negative 1. A cosine function to the negative 1 is 1 over cosine. 1 over cosine is secant. So that I just explained, these are equivalent. I think I just explained why. It has to do with that negative 1 power. Similarly, so let's what are we doing here? Do we know how to integrate a sine? By the way,
Yes.
I'm going to use u. Do I know how to integrate a sine u? What's the answer? Negative cosine u? Do I know how to integrate a cosine u?
Sine.
I think that's sine u. So we had this 3 or 4, 5, 6 days ago. We had this from 5-1 maybe. I mean, they taught me those two. So now I'm saying they're teaching me the other trig ones. So we just stumbled into tangent. You know how to do a tangent? I know how to do it now, but if I wanted to, I could just memorize that it's this. Instead of x's, I'm using u's. It's okay, right? You can use any letter. Okay, guess what? So similarly, cotangent. You could do cotangent, and you would do it the same kind of way, except cotangent's the reciprocal of tangent, so it's, instead of sine over cosine, it's cosine over sine, and then you do it the same kind of way. I think you get the natural log of sine u. I don't think you get a negative sign. All right, there's 2 more. Here's the other 2. Secant. How the hell do you integrate a secant?
That was hard.
There's a method to it that I'd rather not tell you. Can you just believe me that the answer is this? The natural log of secant u plus tangent u. Or would you like to see the proof?
It's hard. I'm trying to come up.
So these, listen, we eased into 5-7, where the focus is kind of this natural log idea. And this natural log idea leads us to these, look, these last 4 new integrals involve natural log. Okay, here's the other one, cosecant of u. The cosecant of u is negative natural log of cosecant u plus cotangent u. There's sort of some patterns here if you'd like to memorize these. You can sort of see the patterns. Again, you don't really have to memorize these because you kind of know how to do them. I sort of just taught you. I didn't teach you how to do these though. I said memorize them, I guess. You could look at the book, maybe you could find how they could prove you this, or you could ask me later, but I just don't want to do it right now. All right, so what I'm doing is I'm cleaning up some ideas. I'm toward the end of 5-7. I got a few minutes. I'd like to keep talking. I know you're in vacation mode, but just chill. Just chill a minute. We'll be in vacation in 10 minutes. That's a lot of new stuff then, maybe to memorize, I guess, or whatever. 4 more things, I guess. Okay, so let's talk about this real quick. Okay, so so when it comes to adding up rectangles, what I did one day is I walked in here one day and I added up some rectangles. I tried to teach you that, and I haven't done any since. But what did I do that? One day I came in with a function and I said, let's do these 4 rectangles, and I did the inscribed ones, then I did the circumscribed ones, then I did the middle scribed ones, then I actually did the actual area under the curve by doing a definite integral. I mean, I did those 4 things. I did the inscribed, the circumscribed, the middle scribed, and then I actually did the damn integral. That was the point. So that was a good lecture one day. It's on video. Then the homework was, when you do the homework, they had that kind of stuff. They didn't want you to do it all in one problem like I did. They had some problems they wanted you to do inscribed. They had some problems where they wanted you to do circumscribed. They had some problems where they wanted you to do middle scribed. So that's what they had in the homework. If you tried it, I don't know. It was just a little 5-2 adding up some rectangles. So then on yesterday's quiz, or the quiz the other day, I don't know, you made that problem way too hard. A lot of you made it way too hard. What I gave you was, I gave you a picture, and I gave you the rectangle. So you didn't have to do anything. There was 4 rectangles there, and all you had to do was, their width was, can you tell me the width of each rectangle? Okay, good. So the width was easy. So the width was a 2. And then you just needed the height. So you needed the height of this middle scribed rectangle. Well, it was in the picture. You could have just looked at the picture maybe and saw that it looked like about 1.5. And this one was about, anyway, this ain't the right picture. But one of them was 3.5, and another one of these was 1.5, and another one was 0.5. I mean, you could just see the heights real easy. So then can you multiply heights times widths and add them up? That was all you were supposed to do. Some of you actually tried to integrate, but when the directions say add up some rectangles, then I don't want you to integrate. I mean, I want you to add up 4 rectangles. It was really easy, and some of you made it a lot harder. The other thing you did was you tried to find these heights by plugging in numbers to find heights. You could have found the right heights. The function would have given you the right heights, but you did weird things. Oh, maybe you weren't in radian mode. Yeah, you better be in radian mode when you're messing with the trig function. Maybe you were getting the wrong heights because you were in degree mode or something like that. Anyway, it was supposed to be kind of easy. The answer was 14. You could, on your quiz, you could check that again. And it wasn't worth that many points. It didn't cost you too many points, but it should have been easy points. It should have been the width times the height, the width times the height, the width times the height, the width, and add them up. And I'm saying you could have seen the height. Right. You could have seen it. But if you didn't trust your vision on the height, then you can get the height by plugging the x value into the function. But you did make some errors doing that, I think, some of you. So, so now, while we're on the top, so that was supposed to be easy. Anyway, if you see it again, it might be easy. If you see it on a test or something. Let me, I want to say something else about rectangles while we're on this topic. Just listen to me a few minutes because it's time to go almost. We skipped section 5-6. But I just want to tell you what it is. Let me just tell you something. So what happens in 5-6 is, again, I can do rectangles and add up rectangles. I learned that in 5-2. In 5-6, they say, you know what? You can do trapezoids. And so they think that's better than rectangles. They think trapezoids are better. What they say is, for this first rectangle, connect this with a straight line. Connect this with a straight line. It's not connect this with a straight line, connect this, and that makes a trapezoid. That's called a trapezoid. And then they got this fancy formula, and it's called the trapezoidal rule. Instead of inscribed rectangles, instead of circumscribed rectangles, instead of middle scribed rectangles, you can do trapezoids. And they think it's better. And we learned that those middle scribes are pretty damn good. That's one thing we learned. Those middle scribes are pretty damn good. And of course, it always is better when you do more rectangles. Thank you. It's a lot better when you do more rectangles. But they say the trapezoids are pretty cool. So there's this rule called the trapezoidal rule. But I skipped it, and it's a funny formula. It's kind of more complicated than rectangles because it's trapezoids. Are you with me? Okay, let me show you something else that's in 5-6 that I skipped. Watch this. So the trapezoidal rule. There's another one. See, this is called numerical integration. By the way, you know, someday in some engineering class, you might have to write a program that does some of this. Okay? I mean, I don't know. They do stuff like that to you. And also, by the way, you can't always integrate everything by hand. And so sometimes you need a numerical estimate. And the rectangles do a good job of that. But they're saying trapezoids would do a better job. Okay, one more numerical method. Watch this. They call this Simpson's rule. Simpson's rule. This is a trick. Instead of rectangles and instead of trapezoids, they say this. From here to here, find the best fit parabola. So, god dang it, you got little curves. But they're parabolas. They're x squared. They're second degree curves that live here. They say find the best fit parabola that fits that. Find the best fit parabola that fits that. Find the best fit parabola that fits right here. And use the area under these parabolas. I mean, they think that's better than, that's less error, probably, than rectangles. Don't you think, maybe?
Yeah.
But it's a pain in the ass. I mean, it's super hard. And anyway, I could drive the formula and show you, but then it turns into this formula called Simpson's rule. So I don't want to do that. Again, when you cut to the chase, we can get the exact area by doing an integral. I mean, we just do a definite integral. But again, not everything can be integrated. So at some point, you do resort to estimation with some kind of numerical method is what it's called. But anyway, we skipped that. So I'm done today. Let's see, what do I have? You know what? Can you hang out 1 second?